Welcome to section 12.4 in your chapter 12 video lecture series, and in this video we are going to discuss the action potential. So we are going to talk about electrically active cell membranes. When we have an excitable membrane, that means we can demonstrate how changes in the membrane can constitute a signal. Our cells are going to produce electrical signals called action potentials that we've kind of talked about in the previous sections. And our electrical properties are going to result from ionic concentration differences across the plasma membrane and permeability of that membrane. So this is picturing for us an axon, and normally we're used to thinking of a cell membrane as being a boundary in a round cell. So a neuron is still a cell. It's still going to have that plasma membrane. So here in the axon, we actually call this an exoplasm, but this is our cell membrane. So along here, we're going to have a bunch of different receptors that are going to allow ions to pass through, and that's going to change the electrical properties inside of our cell, our nerve cell here. So let's talk about some of those properties. We have different ion concentrations inside our cell and outside of our cell. So in this illustration here, we could see this is outside of our cell or extracellular, and this is found inside our nerve cell or intracellularly. So let's first talk about two processes that are going to help set these ion concentrations in here. First, we have our sodium-potassium pump. Remember, we pump well, that's not the right receptor, but imagine we have a pump here. We're going to pump 3 of the sodium ions out of the cell, and 2 of the potassium ions are going to move into the cell. And something else that'll keep this ion concentration is just membrane permeability. We'll have certain channels like leakage channels that'll allow certain ions to randomly move across to either side. And we want to note the high concentration here of sodium and chlorine ions outside of the cell, and the high concentration of potassium and proteins, which are represented by the letter A here, on the inside of the cell. So we have some steep concentration gradients here, and I like this illustration here to demonstrate that, where we have lots of the sodium and chlorine outside of the cell and lots of potassium inside of the cell. So as I mentioned in the previous slide, we have these large proteins inside of the cell. They are not going to dissolve in the phospholipids of our membrane, and our proteins are negatively charged. So here our potassium ions are really attracted to these large negative proteins. Now chlorine is repelled by these proteins, and they're going to exit through these always open non-gated calcium channels, which aren't really pictured here. So they'll always be outside of the cell. And we have some gated ion channels that are going to open and close because some sort of stimulus takes place. And when they open, they're going to change the permeability of the cell membrane, and we're going to use this in order to achieve an action potential. So let's go ahead and review some of the different channels and receptors that we have along cell membranes. So first we'll talk about gated ion channels. What that means is that they will open and close because of some sort of stimulus taking place. And when they open, they will change the permeability of the cell membrane. We can also have ligand-gated channels, which are pictured over here, and you should already be familiar with this type of channel, but they are going to open or close in response to a ligand. So in this case, we're using the example of acetylcholine. Acetylcholine will bind to the channel, and by binding it, it will open that channel and allow certain ions to move through. The other type of channel we have is a mechanically gated channel. This is going to open because of a physical distortion of the cell membrane. Maybe we sense a type of touch or a stretch within this cell membrane, and that is what's going to cause this channel to open, allowing ions to move through. The next type of channel we have is a voltage-gated channel, and these are going to open and close based on a small change in voltage across the cell membrane. So at rest, we're going to see the membrane is negative on the inside compared to the outside. And when the cell is stimulated, that relative charge changes, and the voltage-gated ion channel is going to open or close depending on what the signal is. And so the most common voltage-gated channels will be sodium and potassium, which we will discuss in description of our action potential getting started. Now, the last type of channel we're going to discuss is a leakage channel, and there are many more of these for potassium and chlorine than there are for sodium. So this is why potassium is able to move through more easily than sodium is. So how are these ions moving? We talked about how proteins are going to repel the chlorine because they're both negatively charged. So the chlorine is going to want to move to our extracellular space. And potassium are going to be higher in concentration inside than out because they are going to move from that extracellular matrix toward the negatively charged proteins because potassium is positive. These leakage channels are just going to open and close at random and will contribute to the resting membrane potential. Now, the number of charged molecules and ions inside and out of the cell are nearly going to be equal. We've talked about how the potassium is higher inside the cell, and outside of the cell we have sodium that will be higher. And this creates a potential difference, meaning an unequal distribution of charge between the immediate inside of the cell and the immediate outside of the cell. So you can see here we've represented this by the plus signs. We're more positive here in our extracellular fluid than compared to the inside of the cell in the systole. And this can be anywhere from -70 millivolts to -90 millivolts. But we say that the resting membrane potential is approximately -70 millivolts. And at equilibrium, we're going to see little movement of the potassium and other ions across that plasma membrane. We will have movement of that potassium out through the leakage channels, and movement of ions is due to the attraction of those trapped proteins. But we know that we have leakage channels that are working in both directions. And the movement of the ions really depend upon a concentration gradient. So wherever there is a lot of a certain ion, it's going to want to move to an area where there is less concentration of that ion. And our sodium, chlorine, and calcium that are found extracellularly don't have a great effect on the resting membrane potential since there are few leakage channels for them. And if the leakage channel alone were responsible for the resting membrane potential, in time that sodium and potassium concentrations would eventually equalize. So we wouldn't see that polar difference that we have here, that's positive outside and negative inside. But they are going to be maintained through this special sodium-potassium pump that we find in the membrane. Remember that we're going to have 3 sodiums attach here and move out of the cell, and then the part that we're seeing over and over again right now is these potassium ions attaching, and they would move inside of the cell. And in order to do this, we are going to need ATP. This is an active transport process. Now let's move on to talk a bit more about action potentials. First, we will define depolarization. That is going to be a potential difference that becomes smaller or less polar, meaning that we are moving from our resting membrane potential that's -70 and becoming more positive. Whereas hyperpolarization is a potential difference that becomes greater or more polar, meaning we're becoming more negative and creating even more of a difference here in polarity. Polarity, like think of different charges, right? So as the inside here becomes more positive, we're becoming more like the outside of the cell. Okay, there we are. And so our potassium concentration gradient is going to change based on these different types of polarizations. So if extracellular concentration of potassium increases, then we have less gradient between the inside and outside. So we are depolarizing. We're becoming less of that opposite charge. And if the extracellular ion concentration of potassium decreases, then we have a steeper gradient, meaning we are more of the opposite and we get hyperpolarization. So it's going to be even harder now if we have hyperpolarization take place to reach that threshold to get an action potential to take place. So what we're seeing is that potassium membrane permeability is going to change to cause this to take place. When our cell is at rest, in our resting membrane, potassium in and out is going to be equal through the leakage channels. But there are also gated potassium channels in the membrane. So if those open and more potassium diffuses out, but this is opposed by a negative charge, that starts to develop as potassium diffuses out. And now let's talk through this graph here as an action potential takes place. So at the number 1, we can see that our neuron is at rest at negative 70 millivolts. And at the number 2, some type of stimulus is applied. Let's say you are touching a hot stove, right? That's your stimulus, that heat is coming in. And at that point, we'll see that the membrane will begin to depolarize a little bit. And that membrane voltage is going to reach threshold, and then we start to see a rapid rise toward positive 30 millivolts. And then the membrane voltage is going to start to return back to its negative value. So we're trying to get back to that resting membrane potential. So this, where we become more positive, is depolarization. When the voltage falls, that is called repolarization. And that is going to continue past that resting membrane potential. Remember, we called this hyperpolarization or after potential. And then through that sodium-potassium pump, we can get things to where they need to be and get it to return back to its resting value shortly after that hyperpolarization phase. All right, now our action potential was initiated at the beginning of the axon at what was called the initial segment, and our action potential is propagated. Remember, that means traveling, because more voltage-gated sodium channels are open as the depolarization spreads. So I want to make something clear about these voltage-gated channels. Let's go back to this graph over here. So when we're at rest, those voltage-gated channels are closed, and we only have those leakage channels maybe open and our sodium-potassium pump working. So once we get that stimulus applied, we maybe got those acetylcholine receptors to open up and allow some sodium in, and that made the inside become more positive. Now those acetylcholine receptors are ligand-gated receptors, okay? So here we had leakage channels open. Here we maybe get a ligand-gated channel to open, letting sodium in. Let's say that allows threshold to be reached, and at this point, when threshold is reached, we are going to open voltage-gated sodium channels. So all those gated channels are opening because our voltage inside our cell changed from negative 70 to negative 55. So now that my voltage-gated sodium channels opened, all of these sodium channels are opening and allowing the sodium to flood into the cell, and that's why we get this rapid rise inside my cell to reach positive 30. At the peak here, my sodium voltage gated channel doors are going to close. So I have to take a minute and draw these in. So imagine those voltage gated channels are like doors. So here my sodium door is going to open. That allows all the sodium to move in through that door. And then here my sodium voltage gated channels, or my door, is going to shut. Instead, we have another door that is going to open, and that is going to be my potassium voltage gated channels. So because I reached positive 30, that's what causes these potassium voltage gated channels to open, these doors to open. So now all this potassium is going to rush out of the cell, and that causes the inside of the cell to become more negative. And here, where we do get some hyperpolarization, finally my potassium doors are going to close. My voltage-gated potassium channels are going to close. And that's what allows that sodium-potassium pump to get that resting membrane potential to go back. So I hope my little doors helped you. Another thing I wanted to draw in before I deleted that was that the potassium door here is closed as well. Okay. Now let's move on to talk about this action potential propagating. Because as we're continuing, more of those voltage-gated sodium channels are opening, and that's how we're able to spread that depolarization and continue down the axon. And in an unmyelinated axon, this is called continuous conduction. Now, when we have an action potential taking place here, this portion behind it that has the potassium doors open is going through a refractory period, meaning that that area is not going to be able to have another action potential take place. So we have two types of refractory periods. We have an absolute and a relative. The absolute refractory period you could see here outlined in purple. That is taking place while we have depolarization and repolarization in motion. So here we have a complete insensitivity to another stimulus from beginning an action potential until toward the end of repolarization. No matter how large the stimulus is, a second action potential can't be produced. Now here in the pink, we have our relative refractory period, and this is going to need a stronger than normal stimulus in order to make it to the threshold for an action potential to begin, because we're not even at resting membrane here, resting membrane potential. We are at a more negative state. So now we need a stronger stimulus to make the inside even more positive to reach that threshold for an action potential to take place. And then within our myelinated axons, that propagation of an action potential is going to take place through something called saltatory conduction. So here where we have an action potential taking place at the nodes of RANVA, so this is really where action potentials are going to take place. They skip through the myelin sheath. So anyway, where this action potential is taking place, we are going to get local currents that are going to flow to the next node of RANVA. And so we start to get this propagation that is going to take place. And so once we reach threshold at each of these nodes of RANVA, we are going to get that action potential to take place, and then it'll go on to the next, so that it'll continue along the entire axon. And now just to talk a little bit about some homeostatic imbalances in specifically regarding potassium concentration. Our astrocytes, which if you remember is a glial cell within our central nervous system, is going to maintain a chemical environment in the central nervous system. If our patient is suffering from a stroke or some type of ischemic event, then our extracellular potassium levels are going to become elevated. And our astrocytes sometimes can't keep up with balancing these ions out. So we get this imbalance that takes place. And sometimes these effects can be irreversible. These events are negatively going to affect the internal chemistry of our cells and prevent them from functioning normally.